Okay, let's get busy with the real numbers. It's the last one. Yay! Okay, thus far we've investigated decimals that terminate and decimals that repeat, but there is one final category, and that is a category of decimals that neither repeat nor terminate, and they're called irrational numbers. It's an infinite set, and there's a very, very famous irrational number that you're super familiar with and you've known since you were a child, and that's pi. Now, we often discuss that pi is 3.14 or 3.14159, or even in some circles they say it's 22/7. But these are all approximations because the actual digits of pi are infinite. In fact, I think most recently they've been able to compute it up to about 22 trillion digits, and still there's no repeating patterns. It looks like it's not tapering off, stopping, or anything like that. It's really interesting. And there's more than one of these irrational numbers that kind of come up naturally in computations besides pi, and it's called the Euler number, and it's named after a famous mathematician, and it is denoted by this number E. And it is a number that is infinite, non-repeating, non-terminating decimal, and it has tons of applications with logarithms and exponential equations used heavily in biology, many sciences, in financials, and statistics. Definition: a real number is any number that can be represented as a decimal. Cool. Remember that whole numbers can be represented as a decimal by just putting a decimal point and a zero behind it. The set of real numbers is the union of the rational and irrational numbers. The definition of the square root of a non-negative number a is the number x such that x squared is equal to a. That's what a square root is. If a is a non-negative number, the principal square root of a is denoted by the square root of a, which I have written here, and is the non-negative number x such that x squared is equal to a. I'll explain later in the next slide. The symbol here is called the radical, and the a is called the radicand. We casually refer to a as the number under the radical, and I even more casually refer it to as the guts of the radical. I like to call it the guts. It's fun when you use kind of you have to use like the really natural and important terminology and definitions in class, but sometimes it's fun to go a little bit off brand, especially when you're introducing something, and maybe call it something fun like the guts. Kids will go, oh, the guts. Anyway, here's an example. If x squared is equal to 25, that means we want to know what number multiplied to itself is equal to 25. I want to remind you that anytime we say x squared, that's equal to x times x, just like if we were to say 3 squared, that is equal to 3 times 3. That's what that notation means on the number. It tells us that it's actually an operation. Okay, so we know that 5 times 5 is 25, but we also know that negative 5 times negative 5 is 25. So there's actually two answers to this problem here. So it's super important to make the distinction between solving an equation involving square roots, so using square roots to solve an equation, and evaluating an expression with a square root. So our examples here are going to be solving using the square root. And when we're solving to use the square root, there are going to be two solutions. All right, so our first one, we need to kind of set up the equation. It says find the square root of 144, and to do that we set up the equation of something squared is equal to 144. Now this is similar to this equation that I've written up here, and so we're already getting the idea. The idea is what number times what number equals 144, and we know that x is equal to 12, because 12 times 12 is equal to 144, but we also know that x is also equal to negative 12, because a negative times a negative is a positive, and negative 12 times negative 12 is also positive 144. So in this case, we have two solutions. X is equal to 12 and x is equal to negative 12. Okay. Same thing with this next problem. It's already written and given to you as an equation, so we don't need to do anything much more than to see that x can equal 10 and x can equal negative 10. In elementary grades, you're mostly going to encounter evaluating square roots, okay, and beyond that, but this is really, you won't be solving so many of those equations. However, I want to remind you that from the beginning, when you first get introduced to multiplication of whole numbers, your students are going to be practicing and working on squared numbers, cubed numbers, so that they can recognize these special numbers, okay. So let's look at the steps to evaluate a square root expression. First, you find the prime factorization of the radicand. Then you group the factors into groups of 2, and then each group of factors, of 2 factors, is represented outside of the radical as 1 outside, because it takes a pair to get that number, and then any prime that does not fully group up remains under the radical. So let's look at a couple of examples here. 36, if we were going to find the prime factorization of 36, 36 is 4 times 9, so this is 2 times 2 times 3 times 3. And because we're dealing here with square roots, we're going to pull them out in groups of 2. So there's one group of 2 2's. That's going to come out of the radical as 2. And there's a group of 2 3's going to come out of the radical as a 3. And then they're all going to be multiplied together on the outside. So the square root of 36 is equal to 2 times 3, which is 6. Now another way we could look at that is looking at the squares, the fact that 6 times 6, and we'll talk about that here in a minute. The next one is the square root of 81 over 49. So 81 is 9 times 9, and 49 is 7 times 7. This is actually what's going on inside the radical still. And the way we pull it out of the radical is groups of 2. And we have 2 9's we can pull out, which will become a 9 in the numerator, over, and we have 2 7's we can pull out, which will become a 7 in the denominator. So that one breaks down real nicely. 250. Let's break down 250 because it's not a squared number, and I know that. The 250 could be 2 and 125, and 125 is 5 times 25, and 25 is 5 times 5. So 250 is the square root of 250 is the square root of 2 times 5 times 5 times 5. And we're going to pull these out in groups of 2, and here I have 2 groups of 5's. But I actually have a 2 that does not have a 2 to group up with, and a 5 that does not have a 5 to group up with. So those 2 are going to remain under the radical. The one group of 5 that we do have is going to come out as a 5, just one 5, and then we're going to be left with the square root of what's left over here. And we had a 2 left over and a 5 left over. Those will be multiplied together. And so when we clean this all up and get it all together, we have the 5 on the outside, square root of 2 times 5, which is 10. Another method that's widely used is looking for squares. Like I mentioned in the last slide, from early days, you're going to be reinforcing your students multiplying these same numbers together and identifying squares and cubes and things like that. So that's a real effective way to do this. Remember, you're not really going to be doing these square roots kind of things until the end of 4th, maybe 5th grade. So you know, this is a little bit further up the elementary school math trail, as we would expect it to be, being the last lecture. Okay, so let's look at the examples I have here. I've got the square root of 75, and I happen to know 3/4 is equal to 75 cents. So I kind of used that knowledge and said, oh, well, 75 is 3 times 25. I broke those into their individual radicals, which we can do by the rules of radicals here. And we'll see that the square root of 25 is equal to 5, because 5 times 5. Notice right now it's not plus or minus 5, it's just 5. We're taking the positive answer, the principal solution, or what we called in a couple of slides ago, the principal square root. The principal square root when evaluating. If we didn't decide that we were going to use the principal square root when evaluating, it would be very difficult, because we would always have 2 answers, and that's not really the case. Okay, now let's look at this square root of 900. That's the square root of 9 times the square root of 100, which is 3 times 10, which gives us 30. That one's nice. This last one here is not a perfect square numbers here, so we're just going to start breaking it down. I see that there are 2 zeros on the end, so I know I'm being multiplied by 100, and I have 288 times 100, and 288 looks pretty easy to divide 2 into, and we're blessed with the fact that we get a squared number and a squared number. So 144 is equal to 12. The square root of 144 is equal to 12, and the square root of 100 is equal to 10. So we have 12 times 10, and notice that there was nothing to hook up with our square root of 2, so it just remained under the radical. There are not just square roots. In fact, there's an infinite number of roots. There's cube roots, fourth roots, 67th roots, 128th roots. There's any number you can think of, we could have that kind of root. And what the root tells us, that index, that's the number, and the crack that we're going to talk about here tells us is how many need to be in a group. So because the solution of x squared equals 25, we use a square root to find the solution here. For the non-negative solution, we can extend this to other powers. So if I had x to the 4th equals 25, then the way I would write that non-negative answer would be the 4th root of 25. And here the 4, notice it is small and tucked in the crack of that radical. It's called the index of the radicand. And the index lets us know how many need to be in that group of primes to be able to pull it out. Let's take a look here. Here we have the 4th root of 81. Okay, and this tells us we need to have 4 of whatever prime it is to pull out here. Well, 81 is equal to 9 times 9, so 81 is equal to 3 times 3 times 3 times 3, okay? And we need to pull it out in groups of 4, so we have one group of 4 3s, and so this is going to be equal to 3. Let's take a look at this next one here. I have 648. If we write out the prime factorization of 648, which I did here so I don't have to crank it out there, that's going to be 2 times 2 times 2 times 3 times 3 times 3 times 3. So that's what we get here, and now we're pulling out here. This indicates we need groups of 3 identical primes. All right, so here I have one group of 2s, and I've got another group of 3s. So 2 times 3 will come on the outside, but note we have one guy left over. So when we write this, we're going to have 2 times 3, and then we're going to be left with, and this never changes. If you start off with a square root, it ends in a square root. If you start off with a cube root, it ends with a cube root, and such. You never change the index of the radicand. It never changes, and then we'll be left with what's left over, that 1, 3. So the answer here we can write as 6 cubed roots of 3. What I've done here is I took the square root of 8, the square root of 108, the cubed root of 108, and the fourth root of 108, so you could just see how that kind of worked out. I'll just let you just notice that. Notice the fourth root of 108. No groups of primes came out. That makes total sense because the prime factorization of 108 is 2 squared times 3 cubed, so there's no groups of 4 of anything we can actually take out. Another way to simplify radicals is by taking each of the prime factors separately and dividing the exponents by the indexes, okay? The quotient part becomes how many of those primes are represented outside of the radical, and the remainder is how many of those primes are left represented on the inside. So let's take a look at this cube root of 345,744,000. Okay, I have prime factored it out completely, and I wrote it in terms of those exponents. Okay, kind of in that really neat form there. So we see that this number is equal to 2 to the 7th times 3 squared times 5 cubed times 7 to the 4th. So I broke down each one of our factors here. And I have down this column the powers of each factor. And this, notice it's all the same number, is the index of our radical here. All the same number. And then I do that quick division. 7 divided by 3 is 2 with 1 left over. So I was able to pull 2 out with 1 left over. Now I noticed that I've made a mistake here, and let me correct my typo. This should be a 5. And I'm not sure why I wrote a 3 in there other than it's the last lecture. And I've just made a mistake, so I corrected it now. So let's look at the 3's here. So there are 2 3's, 3 squared. And 3 goes into 2 0 times, so there are no 3's pulled out here because there was not a group of 3's. So it had to remain. Okay, now let's look at the 5. When we take a look at the 5 here, we say 3 goes into 3 one time. So there's just this 1 5 on the outside and no 5's left on the inside. And finally, as we look at the 7 here, 4 divided by 3, so we'll get 1 7 on the outside with 1 7 left on the inside. And then we'll just multiply together. There is a distinction between odd and even indexes, commonly called odd and even roots. For even roots, there is no solution for x squared is equal to -4 or x to the 4th is equal to -8 or any of that. There is no solution when you have an even index equal to a negative number. So n of a equals negative number is no solution when n is even. Okay, Okay, there's no solution when n is even. Okay, and we know that because to get an exact pair, they have to be the same of sign. And when we're dealing with even numbers, say 2 digits, to get a negative, we have to have one negative, one positive, and those are not exact. And we can extend that out to anything, like to the 4th, to the 6th, to the 8th, and so forth. However, when we look at odd roots, that's different, right? And here's my example here. X cubed is equal to -8. Now, when we had x squared equal to -4, we only had x is equal to -2 times 2 or 2 times -2. Never the same here. So how can we figure out -8? Well, -8, how can we multiply that out? Well, it could be -2 times +2 times +2. That equals -8. But these are not exact primes because the signs are different. Okay, these aren't exact. We can't do that. So let's look at another way we could write it. -8 is equal to -2 times -2 times -2, because -2 times -2 is +4 times another -2 makes a -8, and that gets us for us. And check it out. Here we do have exact primes. They just so happen to be negative. So the answer of the cube root of -8 is -2. So we can state a rule here. If n is even, the nth root of a is going to be the absolute value of whatever. In other words, always, and I do mean always, a positive answer. But if it is odd, it could be positive or negative. We just saw that the cube root of -8 is equal to -2, but I want to tell you that the cubed root of +8 is actually equal to +2. So I don't want you to immediately assume that if it is an odd index that it's negative. That's not true. You really have to work it all the way out and see how it's going to fall out at the end. Finally, the properties of the reals follow the properties of whole numbers, like the associative, commutative, distributive, the additive and multiplicative identities, depending on what we're talking about, right? The additive identity of being 0, the multiplicative identity of being 1. And also, interestingly, real numbers also have that density property that we have with rational numbers, where we can always find that fraction between two fractions or that decimal between two decimals by going out to more exact, further out with the decimal point, bigger with the denominator, either one, we can always find that other one. And we can actually do that with irrational numbers too. So we want to find a repeating decimal between the square root of 2 and 1 4/9. This seems really odd. Not easy for you to see that, right? So anytime you're doing comparisons, you have to compare apples to apples, right? So we have to compare them in the same form. So we're going to turn both of these numbers into decimals. So I converted the square root of 2 by my calculator, and I found that it is this number, 1.4142135623 ... Remember, this is non-repeating. It's irrational. Square roots are irrational numbers unless you've got that perfect square root, like the square root of 4. That gives us the answer of 2. That's kind of perfect. But most irrationals, most square roots are not perfectly done. Most of them are going to have something left over on the inside, forcing them to be irrational. So I've written out the square root of 2, and then I wrote out 1 4/9. And 1 4/9 turns out to be a repeating decimal of 1.4 repeating. So I wrote it out, and I actually wrote out a bunch of decimals there just so I could really kind of compare the two. Now, I couldn't exactly get these guys to line up nicely, and frankly, I couldn't. But if you're in the classroom and you're actually writing it down, you can easily line it up. I just didn't have the patience to mess with it. So there are infinite, I mean infinite answers in between these two, just like there are infinite answers in between any two decimals or infinite answers between any two fractions, okay? So this is infinite. I only gave you 3 of the options that I came up with. One being 1.4, and just make all the 2's repeat. Another being 1.4242424242, make that repeat. Or 1.434343, we could do that. But also, I kind of got in my head, I was like, well, I could do 1.414 and then repeat out there. I mean, there is so many options. I could do 1.43 and only repeat the 3. There are infinite options to come up with numbers in between the two. Now let's take fractions, which most people don't like, and put them into an exponent, because they'll definitely hate them there, but I really enjoy them. I think that it's kind of interesting how fractional exponents relate to radicals. All right, so if we take a real number and we raise it to a fraction, here are the rules that we get to follow. If x is a real number and n and m are integers with no common factors, and n is a positive integer, okay, so it's greater than 1, then these rules we get. In other words, x to the 1 over n is equal to the nth root of x. And I know it says when the nth root of x is meaningful, and that just kind of means this is a general statement, but this might not actually be meaningful if x is a negative number and n is an even number, okay? So they just use this kind of information so we can get rules without having all these exceptions or multiple rules, okay? And then again, this other one, x to the m over n is equal to the nth root of x to the m. Now, what I usually show my students in algebra, a way to remember this, is I say that it is in the form of x to the power over index. So we can refer this, because if they know where the index is and they know where the power goes, they can see that that is kind of a mapping. It's kind of a mapping on how they convert them over. Anyway, that's what I do. Here's some more exponent properties, and I wanted to give you an example of each of these. And this first property says x to the negative r, and so an example of that could be something like 5 to the negative 7. That's equal to 1 over 5 to the 7th power. So one thing I want to say is negative exponents flip your fraction over. Okay, and remember, no matter what you have, whole number or not, it is always a fraction. So I'm going to say negative exponents flip your fraction over. I forgot an R. And so that would also be true if we had a fraction. I'm just going to do another example here. If we had a fraction of 1/2 to the negative 3, that's going to be flip your fraction over, basically 2 over 1 to the third power, which is equal to 8. Stay, change, flip is kind of like the idea here, because this in the middle is 1 over 1/2 to the third, which takes us there because we flip it over. Sorry, I left that out. Anyway, almost done. We have 2 slides left. I'm not losing focus now. If I do, I'm just sticking with it. So let's look at this example here, just so we could see. If I had, say, 8 times 4 to the 1/2 power, that's going to be 8 to the 1/2 power times 4 to the 1/2 power, which we could rewrite as the square root of 8 times the square root of 4, which we could also rewrite as the square root of 8 times 4. So there's the way to convert it from fractional exponents into a radical, which would then be, of course, the square root of 32. Haven't simplified it. I'm just showing you how this rule works all the way across. And here's another example. We'll do this guy. We'll do something like 3/10 to the 1/5 power, just for the fun of it. That's going to give us 3 to the 1/5 power over 10 to the 1/5 power. That's equal to the 5th root of 3 over the 5th root of 10. Now notice we can write it all these different ways, and we can also write it all as 1. Sometimes it is beneficial to write it separately, and sometimes you want to write it all together. It just depends on your application and what you're doing with it. And then this one here, I love this. This is used a lot. So if I said 5 cubed raised to the 1/6 power, say, this is going to be 5 to the 3/6 power, which is actually equal to 5 to the, I shouldn't have used ones that turn out nice. Hold on, let me redo that example. Let's make it to the 1/5 power or something, or 1/8 power. Some number that doesn't reduce is my problem. It was going to reduce, and I wanted you to see it not reducing. So this is equal to 5 to the 3/1 times 1/8, 3/8 power. And if we were going to rewrite this in the radical notation right here, remember that this is the power over the index if we want to think about it like that. So we'll have 5 cubed on the inside, and this will be an index of 8 on the outside. We wanted to write it all looking pretty. It would be the 8th root of 125. No way to reduce that because there's only 3 5s in there. Can't break it down. We need 8 of those 5s to actually break it down. So that is simply as simple as possible. Okay, and then finally, the last examples. Yes, let's do this. I'm stoked. Here we go. Let's take a look at this first guy. This says 16 to the 1/4 power. Now, what we're going to take advantage of, and I'm going to write it over here, is the fact that x to the p over n is equal to the nth root of x to the p. Okay, so in this case, we're going, and the way that I like to do it is I like to say, well, this is the 4th root of 16 to the 1st power. Okay, if that was squared, we need to do some work with that. So that's the 4th root of 16 And let's break down our 16. 16 is 4 times 4, so 16 is equal to 2 times 2 times 2 times 2, or 2 to the 4th. So let me write it like that. So this is 4th root of 2 to the 4th. Now, check this out, because this works every single time. When your index matches the power on your radical, all of that goes away, and you're just left with the 2. Now we know it's just going to be 2 because look, we could do it right here and say that there's one group of 4 2's that we pulled out and done there as well. But I like to show this little trick too. That's a great little tricky poo. It's because they undo each other. Let's look here. 16, so to the 5/4 power. All right, so let's write this out. So we have the 4th root of 16 to the 5th power. Now, I don't know that you want to write out 22's and start doing it. So what we can do is look from here first and just consider the 16. We have 5 divided by 4, 16. So that leaves 1's going to come out, and we're going to have the remainder of 1. So we can do this in more than one step. So my first thing I'm going to do is this becomes 16 4th roots of a 16 left. Now, we've just done the 4th root of 16 over here, right? And we know that the 4th root of 16 from over there is equal to 2, but I'm going to show it this way. 4th root and 16 is 2 to the 4th. I just want to show that happening. And so our final answer then becomes 16 times 2, which is 32. All right, let's take a look at this next one. -8 to the 1/3 power. This is equal to the cubed root of 1 -8. Okay, and we've done this already in this lecture. So the cube root of -8, as we saw earlier, was -2. Let's do another one here. Cube 125 to the 4/3 power. So we have the cubed root of 125 to the 4th power. Again, this is very similar to this 16 to the 5/4 power. If your fractional exponent is not a proper fraction meaning that the numerator is smaller than the denominator, then you want to do this division here. So we can say 125, there are 4 of them, divided by 3. That's going to give us 1 remainder 1. So just like we did here, this is going to now equal 125 on the outside, 4th root of 125 left on the inside. I don't know why I wrote 4th root. I just jacked that up. It's the 3rd root. My bad. The cube root there. And then we know 125 is equal to 5 times 5 times 5, which is 5 cubed. So we could write this continued as 125 is times the cube root of 5 cubed. Those guys go away. Awesome sauceum. And we're left with 125 times 5. And I didn't actually work that out, but maybe it's 625. I got to check that out. I can't do that math in my head right now. That actually looks like a decimal point too. That is not a decimal point. Yeah, it's 625. It's equal to 625. And then the last and final one, and the last and final lecture. I'm so excited. Okay, so this is equal to the fourth root of negative 16 to the first power. And I hope you see right away that this is equal to no solution, because we cannot take an even root of a negative number. We cannot take the even root of a negative number in the reals. Not saying it doesn't actually happen. It can happen, but that's beyond this class. Okay, we've done it. Holy crap. I'm so excited. We got it done. Thank you for bearing with me this week with these lectures. Have been rough because I am exhausted, but we have done it and we are done. And thank you so much, and have a great day.